Come on, my dears, let us proceed further in chapter number 6. Today we will finish the theoretical portion of this chapter along with the illustrations. Okay, kindly read this statement of illustration number 12. Come on, have you read it? Look, we are given one reaction in which the reactant is first initially shown by symbol capital A small m, and it is none but americium. What is that element? Americium. The way we have germanium from the country Germany, same way we have element americium from the country America. Correct? Fine. So this is an element americium which is naturally radioactive because it has atomic mass number, you can see it is greater than 206. So it is naturally radioactive, and it disintegrates and emits one alpha particle, and it gets transformed into daughter nucleus which is neptunium, capital N small p. It is neptunium, not Manchurian. What is it? Neptunium. Okay, fine. Now here atomic mass number is 241, and alpha particle, you know, it is 2He4. Okay, so 241 minus 4, it will be 237. Simple. Fine. Now, just for the sake of simplicity, you please adopt very simple symbols so that you can write very speedily, you can remember, and you can get the final answer very quickly. Okay. So just for the sake of convenience, I just choose this way all the symbols. Look, mass of americium nucleus, I just take capital M. Mass of alpha particle, I take small m1. Mass of neptunium nucleus, I take small m2. Okay, fine. Now for this reaction, you just apply law of conservation of linear momentum. According to that law, mathematically you can write final momentum is equal to initial momentum. Final momentum is suppose vector p dash, initial momentum is suppose vector p. Now in the final condition, we have two components, that's why I am making their vector addition of their linear momenta, vector p1 plus vector p2, and that equals to initial linear momentum, which should be taken 0 vector, because initially this americium nucleus is at rest. Because this initial nucleus is at rest, its initial momentum is 0. Correct? Now this is the momentum of first particle, that is say alpha particle. This is the momentum of this daughter nucleus. Now just transfer from left to right side, from plus it will become minus. And now take magnitude on both the sides. Magnitude of this is P1, magnitude of this is P2. So P1 equals to P2. Okay, fine. Now apply law of conservation of energy. According to that law, whatever is the total energy in the initial state before reaction, same should be same should be total energy in the final state after the reaction is over. Correct? Now here we include energy equivalent to mass also. So if you apply that law for this reaction, come on. First of all, what is the energy equivalent to mass capital M? It is mc square. Correct? You know Einstein's mass energy conversion relation. Energy equivalent to mass m is how much? mc square. But here I have written capital M, which is mass of americium nucleus, into small c square. You must remember what is small c? Velocity of light in vacuum. Okay, and its initial kinetic energy I just showed by symbol Ki, I for initial. Now later on we have two nuclei, so we should add their masses, and that total mass should be multiplied with c square, so that we will get energy equivalent to their combined mass, and plus kinetic energy of alpha particle, which I am showing by symbol K1, plus kinetic energy of neptunium nucleus, which I am showing by symbol K2. Fine. Initial total energy and final total energy should be equal according to law of conservation of energy. Fine. Now this Ki is 0. Ki is 0 because initially this americium nucleus is at rest. Anything which is at rest will have velocity, momentum, kinetic energy equal to 0. So this Ki value is 0, and now transfer this term from right to left. Then capital M as it is. When I transfer this term over here, it will become minus, and c square I am taking common, and that equals to K1 plus K2. Let us find out now K1 plus K2. So I am finding now K1 plus K2. Then I should write first of all here mass of americium nucleus, which is 241.05682. That many atomic mass unit, which is given to you in the statement, minus, come on, this is mass of alpha particle, given to you in the statement is mass of alpha particle 4.002603 atomic mass unit, plus this is mass of neptunium nucleus, which they are given in the statement 237.04817. This many atomic mass unit. But now don't write into c square. In this step you don't have to write the value of c. Listen, tell me what this whole term will give you. Energy equivalent to decrease in mass. Energy equivalent to decrease in mass, and that decrease in mass we have found out here in atomic mass unit. And in the statement you are given that one atomic mass unit is equivalent to 931.474 million electron volt of energy. And so what we should do? We should not write the value of C. We should simply find out this difference in mass in atomic mass unit, and directly that difference in mass should be multiplied with 931.474 million electron volt. Simple? Fine. Now this difference of mass comes out to be this, which is put in this bracket. You can just find out this difference in mass, and that difference should be multiplied with this figure, and final answer is 5.6326. These many million electron volt. I repeat, summation of these two should be subtracted from this. That should be multiplied with this, and that answer is 5.6326 million electron volt. Wait. Now tell me, don't you know kinetic energy formula in terms of linear momentum and mass from first semester? You must have remembered K equals to P square upon 2m. There are three formula for kinetic energy. K equals to half mv square, or half pv, or P square upon 2m. So here I am using P square upon 2m. Now tell me, here for alpha particle and neptunium nucleus, the momentum is same. Because momentum is constant, then P square upon 2 will be constant. If you remove that constant part, then K is right now inversely proportional to this mass. So if there is inverse proportionality relation, then 1 to 2 1, 1 to 2 1. So here I am writing K1 upon K2, and here I am writing M2 upon M1, 1 to 2 1. Simple? Fine. Now K1 as it is. Take componendo in the denominator. So K1 as it is, componendo in the denominator. So I should add this with this. So K1 plus K2. What about right hand side? Here M2 as it is, componendo in the denominator. So here I should write M1 plus M2. Simple? Fine. Now this is kinetic energy of alpha particle which I am looking for. Leave this K1 as it is. What is K1 plus K2? Just now we have found out K1 plus K2 is 5.6326 million electron volt. So that K1 plus K2 value I have substituted here, and that equals to M2, which is mass of Neptunium nucleus given in the statement is 237.04817 atomic mass unit, divided by this is mass of alpha particle given in the statement is 4.002603 atomic mass unit, plus mass of Neptunium nucleus, same value are written here. Now simplify, find out value of K1. It comes out to be 5.539 million electron volt. So this is nothing but kinetic energy of alpha particle, correct? Now tell me how simple it is. All the symbols, everything so simple, you can remember also at once, and you can definitely write it very quickly in the examination, okay? The symbols which they have adopted in textbook is a bit complicated, so don't go for that method. You go for this method. It's very easy, very short, okay? Now kindly read the statement of illustration number 13. Have you read it? Look. Again they have given one reaction ZXA, which is parent nucleus, emits one alpha particle, gets transformed into daughter nucleus, Z minus 2, Y A minus 4, and some amount of energy is liberated, which is called Q value of the reaction. Simple? Fine. This is the reaction they have given. Now here atomic number is Z, here atomic number is Z minus 2, here atomic mass number is A, here atomic mass number is A minus 4. This is parent nucleus, this one is daughter nucleus. Apply now law of conservation of momentum. Then final momentum should be equal to initial momentum. Final momentum means vector addition of momenta of Y nucleus and alpha particle. Momentum of Y nucleus is what? Mass of Y nucleus multiplied by velocity of Y nucleus. Plus momentum of alpha particle means what? Mass of alpha particle into velocity of alpha particle. And that should be equal to initial momentum. Initial momentum is momentum of nucleus X, momentum of parent nucleus. But parent nucleus was at rest, so naturally its momentum would be 0. So initial momentum is 0 because velocity of parent nucleus is 0. Transfer this part over here, from plus it will become minus. And now take magnitude on both the sides. So My Vy will be equal to M alpha V alpha. My Vy equals to M alpha V alpha. Find out Vy, transfer this. So it is V alpha into M alpha upon My. M alpha upon My. Leave it. We will require this result. Wait. Now let us find out Q value of the reaction. Q value of the reaction, you can always find out value if you want to find out. The formula is very simple. Total mass of reactants minus total mass of products, and that difference of mass should be multiplied with C square. The same thing I have written here. Total mass of reactants, right now it is only one, which is parent nucleus X. So I am writing mass of parent nucleus X minus total mass of products, total mass of products. Products are two, Y nucleus and alpha particle. Okay. So mass of Y nucleus plus mass of alpha particle. This is mass of reactant minus total mass of products, and that difference in mass should be multiplied with C square. Correct? And the same formula, another formula for Q value of the reaction is also given in terms of kinetic energy. This is a formula of Q value in terms of difference in mass, but if you want Q value formula in terms of kinetic energy, remember it is just equal to change in kinetic energy. It is just equal to change in kinetic energy. Change means what? Final minus initial. Change means what? Final minus initial. So what is final kinetic energy? For Y nucleus I am writing Ky plus for alpha particle I am writing K alpha. So this total gives me final kinetic energy minus initial kinetic energy is for nucleus X. So I am writing Kx. Final minus initial will give you change in kinetic energy. So you can remember two formula for Q value of reaction. This is the formula in terms of difference in mass. This is the formula in terms of change in kinetic energy. Simple? Fine. Now tell me, this Q value as it is, correct? What is Ky? What is Ky? Kinetic energy of nucleus Y. But what is the formula for kinetic energy? Half mv square. So like that for Ky, I am writing half my vy square plus kinetic energy of alpha particle. Come on, half m alpha v alpha square. And what about kinetic energy of parent nucleus X? It is 0 because parent nucleus is at rest. Parent nucleus before the reaction it was at rest. Anything which is at rest must have kinetic energy 0. So Kx value is 0. Kx is 0. And now this 1 by 2 my as it is. But what about vy square? Vy square, find out from here. Vy square will be v alpha square into m alpha square upon my square. Make it squared on both the sides. Vy square will be v alpha square into m alpha square upon my square. Here it is, v alpha square into m alpha square upon my square. Simple. Plus 1 by 2 m alpha v alpha square as it is. And now my from numerator, my from denominator, you can get it cancelled. And from whatever is remaining, which part you can take common? Come on, 1 by 2 m alpha, only one m alpha I am taking common, into v alpha square, because from m alpha square only one m alpha I have taken out, still one m alpha has been left, and that m alpha I have written in the bracket. Upon one my is getting cancelled, but another my is left. So here left from inside the bracket, from here it is m alpha upon my, plus this whole part is taken out, so left is 1. I repeat, 1 my is getting cancelled, 1 by 2 m alpha v alpha square I just take out, then 1 m alpha is left from here upon my, and this whole term is taken common, so left inside the bracket from here is 1. But what is this 1 by 2 m alpha v alpha square? It is nothing but kinetic energy of alpha particle. So in place of this, I just write K alpha, correct? Fine. And what is this m alpha upon my? That is ratio of masses of alpha particle and daughter nucleus Y. That ratio is given to you in the statement. It is 4 upon A minus 4. 4 upon A minus 4. But what is A? It is atomic mass number of parent nucleus. What is capital A? Atomic mass number of parent nucleus. So this ratio they have given in the statement, which is 4 upon A minus 4 plus 1. Now simplify. K alpha as it is, take LCM, it will be A minus 4. This A minus 4 will be multiplied here. So 4 plus A minus 4. 4 minus 4 will cancel. So left is K alpha into A upon A minus 4. A upon A minus 4. Correct? So this gives you formula of Q value of this reaction. Please remember this formula. It will be useful to you in MCQ, because in MCQ, if it is asked, you will have no time for the derivation of this formula. In that case, they will give you these two values directly. You can put them here. You can find out the value of Q. Correct? What is that formula? Q value of the reaction is K alpha into A upon A minus 4. But come on, Q value of the reaction is K alpha into A upon A minus 4. What is K alpha? Kinetic energy of alpha particle. And what is capital A? Atomic mass number of parent nucleus. Got it? Fine. Now, my dears, we will study the next article, which is very important short note on nuclear fission. What do you mean by nuclear fission? We will study about it in this article very much in detail, but I am just giving you very primary introduction. Nuclear fission means process of breaking of a heavy nucleus and dividing it into two or more than two lighter nuclei. Such a process is called nuclear fission. Okay. Let us see how that phenomenon was discovered. What does history say? Let us see all the points one by one. Okay. First of all, in the year 1932, come on, Mr. Chadwick had discovered neutron. Correct? Neutron, you know, it is a chargeless particle. Correct? Then, in the later time, there was a scientist with name Mr. Fermi. In the year 1939, this fellow, Mr. Fermi, in the memory of whom we have given very short unit of length, 10 raised to minus 15 meter, it is only known as 1 Fermi. The same fellow in the year 1939 had suggested that if we want to carry out nuclear reaction using neutron as a projectile, then it is found to be the best projectile. Neutrons were referred by Mr. Fermi as best projectile. Why? See, there is a reason. Suppose you have a nucleus which is always having positive charge, and suppose incident projected particle is also having positive charge, suppose. Then when projectile has positive charge, naturally it will have to overcome the repulsive force provided by the nucleus. So it cannot go much closer to the nucleus, correct? It cannot penetrate the nucleus, correct? But instead of any other projectile particles, if you take neutron, then because neutron is chargeless, then while going closer to the nucleus, neutron does not require to overcome the repulsive force, because there is no repulsive force exerted by nucleus on the incident neutron. And that is why the neutron can go deeper inside the nucleus, it can penetrate it nicely, and thereby it can just interact very strongly. Fine. Because it can just interact very strongly, neutron is said to be the best projectile. Okay, fine. Then there were two scientists belonging to the field of chemistry. There were two chemists, you can say, Mr. Otto Hahn and Mr. Strassmann. Mr. Otto Hahn and Mr. Strassmann, they were two chemists, and they were performing experiments regarding projecting, they were just making the bombardment of thermal neutrons on the compounds of uranium. What they were doing? They were projecting thermal neutrons, they were making bombardment of thermal neutrons on the compounds of uranium. What do you mean by thermal neutron? Thermal neutron is that neutron which is under thermal equilibrium with the surrounding. What do you mean by thermal equilibrium? Thermal equilibrium means no exchange of heat energy, and that would be possible if at room temperature kinetic energy of neutron and kinetic energy of other atmospheric particles have same value, correct? So, if you find out that kinetic energy of neutron at room temperature in electron volt, it comes out to be nearly 0.04 electron volt. Such neutrons do not give up energy to the surrounding, and they do not absorb the energy from surrounding because their energy and surrounding constituent particles have same energy, correct? That's why that neutron is said to be under thermal equilibrium. But such neutrons which are under thermal equilibrium, they are called thermal neutrons, correct? In short, thermal neutrons have kinetic energy nearly 0.04 electron volt. Fine. Now, when such thermal neutrons were bombarded on the compounds of uranium, in one of such experiments, these two fellows had noticed that they had discovered one very light element as compared to uranium. It was found to be of half the mass, nearly half the mass. That element was none but barium, 56 barium 144. So, these two persons were rather surprised because they just could not explain that out of very heavy nucleus, how could we get such a light nucleus, correct? Nearly half the mass. Then they could not explain this phenomenon. They were very much surprised. Later on, same phenomenon was explained very nicely by one lady physicist and her nephew. The lady physicist's name was Mrs. Mittner, and she had one nephew whose name was Mr. Frisch. These two scientists had combinedly explained the whole phenomenon, and then on the name of Mr. Frisch, this phenomenon was later on known as nuclear fission. So, that word, that name nuclear fission was given after the name of this scientist, Mr. Frisch. He had called this phenomenon as nuclear fission. Okay, fine. Now, if you are talking about nuclear fission of say 92 uranium 235, when it is bombarded by neutron, then there are as such many nuclei which are obtained after the reaction, but out of many such nuclear reactions, in our syllabus we have to study about 3 nuclear reactions. All the 3 nuclear reactions you can write this way very easily. The left side is same for all the 3 nuclear reactions. That's why I have written only once, and on the right hand side there are 3 different reactions. I am showing you. Look, in the first reaction, these two are the fission products. Anything which you obtain as a product in the process of fission should be called fission products. As fission products, we get 2 nuclei. One is 56 barium 144, second is 36 krypton 89, plus this indicates Q value of the reaction. Fine. In the second process, you may get these two. Come on, 51 Sb 133. Sb means antimony. Come on, 41 niobium 99. Nb means niobium. This is Q value of the reaction. Come on, third one, 54 Xe, that is xenon 140, 38 strontium 94, plus Q is Q value of the reaction. Once again, I remind you the names of different elements. Look here, barium, krypton, antimony, niobium, xenon, strontium, correct? If you can remember the names, well and good. If you cannot, don't bother, because in the examination you would write simply these symbols. Okay, fine. Now, In this process, after the reaction, whichever neutrons are emitted in the process of fission are called fission neutrons. Remember, this is projected neutron, this is incident neutron, this is not fission neutron, this is, come on, projected neutron. Okay, fine. Then whichever products we obtain in the process of fission, they are called fission products, and whatever energy is liberated in the process is called fission energy. What are they called? Fission energy. Come on, neutrons are called fission neutrons, products are called fission products, and amount of energy liberated is called fission energy. Simple? Fine. Then out of fission of uranium, so far we have obtained 60 different product nuclei. 60 different fission product nuclei we have obtained out of fission of uranium. Okay, few of them I have narrated here. Correct? Those 60 different nuclei which are obtained as fission products out of fission of uranium are having their atomic numbers from 36 to 56. Atomic number, come on, 36 to 56. Correct? Fine. Then we have observed experimentally that out of many fission products which are obtained out of fission of uranium, if any fission product has atomic mass number 95 or very near to that, or 140 or very near to that, then they are found to be taking place, they are found to be getting formed with maximum probability, with maximum quantity and maximum probability. So fission products having atomic mass numbers nearly 95 or 140 are found to be formed with maximum probability. That's what I written here, maximum probability. Correct? Fine. Many of the fission products, they are found to be radioactive. So they simply do not get formed into directly stable elements. No. They are initially radioactive, and later on what do? They undergo beta disintegration process. They emit successively beta particles, and as they emit beta particles successively, then after losing excess of energy, they become gradually stable. Correct? Fine. That's what I have written here. Fission fragments, they are found to be radioactive. They undergo successive emission of beta particles, and finally they become stable. Okay, fine. Then fission neutrons, whichever you get in the process of fission of uranium, are found to be having very large amount of energy as high as 2 million electron volt. Their kinetic energy is 2 million electron volt, which is very high. As compared to thermal neutron, the kinetic energy of fission neutron is very high. This is simply electron volt, and that too only 0.04. This is 2, and that 2 million electron volt. Okay, fine. Energy obtained per one fission process is found to be approximately 200 million electron volt. 200 million electron volt energy is liberated out of fission of one uranium nucleus. Got it? Now you may have question, in which form do we get this energy? We get this energy in the form of kinetic energy of this fission products, kinetic energy of neutrons, and in the form of energy associated with emitted gamma radiation. So liberated energy is in the form of kinetic energy of neutrons, kinetic energy of fission products, and in the form of energy associated with gamma radiation. Okay, fine. Now whatever is the kinetic energy associated with neutron and fission products, ultimately that is being transformed into heat energy, and after that how that heat energy is transformed into another useful form of energy we will see later on. Okay, fine. The theoretical explanation of this nuclear fission process was given by these two scientists, Mrs. Mittner and Mr. Frisch. These two scientists had given satisfactory explanation of this nuclear fission. They had developed one model. They had compared nucleus with a drop of liquid. Because they had compared nucleus with drop of liquid, they called this model as liquid drop model, which is found to be quite successful in explaining many of the properties in this phenomenon. Okay, fine. Now let us see what is called nuclear chain reaction. Nuclear chain reaction. I am showing you. See, out of fission of uranium nucleus, in some of the fission processes we get 2 neutrons. In some of the fission processes we get 3 neutrons per fission. In some other reactions we get 4 neutrons per fission. So I mean to say number of neutrons generated in these processes is different. On average we find that 2.5 neutron are emitted in the form of fission neutrons per one fission process. 2.5 means is not like that 2 plus 0.5. It's not like that, correct? There cannot be half neutron. There cannot be half neutron. It's not like that. Suppose you consider two processes. In one process, 2 neutrons are emitted. In another process, suppose 3 neutrons are emitted. So 2 plus 3 is 5. Number of process 2. 5 upon 2 will be 2.5. But that does not mean that there exists half neutron. Half neutron cannot exist. This is the figure on average. Okay, fine. Now tell me, suppose in a particular nuclear fission process, we get emission of 4 neutrons, suppose. So how many fission neutrons? 4. Then what you may do? It was suggested by Mr. Fermi in the year 1939 that we can utilize these 4 neutrons further in producing fission of other 4 uranium nuclei. Out of one fission, if you are getting emission of 4 fission neutrons, then out of 4 fission processes, you will have emission of 4 fours are 16 neutrons. Further, your temptation will increase now. Further, you may think of utilizing those 16 neutrons in producing fission of other 16 uranium nuclei, and then you will have emission of 16 fours are 64 neutrons, fours are 256 neutrons, fours are 1024 neutrons, fours are 4096 neutrons, and so on. Further, I don't know. I mean to say that number will increase fantastically, and every time if you can just through some proper experimental setup, if you can utilize the same number of emitted neutrons in producing fission of same number of uranium nuclei, then this whole nuclear fission process can be continued quite long in the form of cascade, in the form of one after another. Then such a long nuclear fission process is only known as nuclear chain reaction. Nuclear chain reaction. And then we will have enormous amount of energy liberated at the end of this process, because out of one uranium fission, out of one uranium fission process, we are likely to get 200 million electron volts of energy. So in a given quantity of uranium, you have very large number of uranium nuclei, and if you can somehow produce the fission of all those nuclei, you will have liberation of very large amount of energy. We will be benefited so much, correct? But then this process is not that easy, especially out of inexperience. When scientists had tried this process initially, they cost their lives also. So this process is that way very dangerous. We must take enough safety features in our mind, and then we should carry out this process, correct? Let us see what are the problems we come across in this process, what are the difficulties we face, and what is the remedy, what is the solution for that. Let us make a brief discussion of that, okay? That's what are written here, problems and their solutions. Come on. in whichever chamber you carry out this nuclear chain reaction process, normally we call it nuclear reactor. Nuclear reactor. Now let us see all these features one by one. Okay. First of all, first problem is this, that neutrons, they have a tendency to escape out of the fissionable material. Fissionable material means uranium. So if neutrons are escaping out of the fissionable material, then they cannot produce further fissions, correct? So we want them to be incident once again. For that, it is necessary to reflect them back towards the fissionable material. In order to make them reflected back towards the fissionable material, we use proper reflectors which are called neutron reflecting faces. Neutron reflecting surfaces. Okay, fine. So we must use proper neutron reflecting surfaces. Fine. Then the fission neutrons obtained are found to be very fast. They have energy nearly, as I told, 2 million electron volt. Now this much highly kinetic, highly energetic neutrons, they cannot produce the fission of uranium nuclei so well. So what we have observed experimentally, that if you can just transform them into thermal neutrons having very low energy, then using those slow moving neutrons, we can produce the fissions very successfully with a very high rate. So we prefer to convert them into thermal neutrons. For that we need to decrease their speed, and for that we use specific materials which can decrease their speed, which can control their speed. Such substances are called moderators. What are they called? Moderators. Moderators are prepared from the materials, come on, simple water, that is H2O, heavy water, that is D2O, carbon in the form of graphite, and beryllium. Carbon in the form of graphite. Carbon in the form of graphite and beryllium. Using these substances, we prepare nice moderators. Okay. Moderators are those substances which can control the speed of neutrons. Okay, fine. Then there is one more problem. Through the surface of fissionable material, some neutrons leak outside. So that leakage process, because it is undergoing at the surface, we call it surface process, correct? Through that surface process, we have loss of fission neutrons. So we would like to use their energy. For that, what we should do? We should minimize that leakage, and practically we find that the rate of leakage depends on such a ratio. It depends on ratio of surface area of fissionable material to the volume of that fissionable material. As you reduce this ratio, then this leakage rate would decrease, correct? So if you want to minimize this leakage, then you should minimize such a ratio, correct? And that is how we arrange the fissionable material such that such ratio is found to be very small. Okay. Then practically we find that fission of 92 uranium 235 can be produced nicely using slow neutrons. As compared to fast neutrons, the slow neutrons can produce fission of this uranium nuclei very nicely, okay, with large amount, with large number, okay. Then here enormous amount of heat is generated because so many nuclear reactions are taking place, and because of very high amount of heat energy liberated, the temperature is likely to increase up to 10⁶ Kelvin also. Now, because of such enormous amount of heat, it so happens that fissionable material, moderators, every substance is getting heated up so much, then we would like to absorb that heat energy and we would like to convert it into another useful form of energy. For that, what we do, we pass some cold substances through the tubes which are inserted into the fission chamber, and then when these cold substances are passed through those tubes, they absorb excess amount of heat energy, and then that excess heat is withdrawn from the chamber. That is how they do the job of cooling down the chamber. because they do the job of cooling, we call them coolants. We call them coolants. And good coolants are made from water, then liquid sodium, liquid lithium and gases. That's what I have written here. Come on, water, liquid sodium, liquid lithium and gases. They are found to be good coolants. Okay. Now, regarding the number of emitted neutrons, we have one problem. To understand about that problem, one definition we require. Let us define that quantity. It is none but multiplication factor. Multiplication factor shown by symbol capital K. Definition is very simple. At any stage during the nuclear chain reaction process, the ratio of number of emitted neutrons to the number of incident neutrons is called multiplication factor at that very stage, shown by symbol capital K. Okay. Now, practically through our experiences, we have observed that if value of K is kept equal to 1, then the nuclear chain reaction process can be completed nicely, keeping it under control also. Successfully we can complete it. If you can keep the value of K equal to 1. When value of K is equal to 1, the nuclear reactor is said to be in a specific condition, which is called its a critical condition. Correct? Nuclear reactor is said to have achieved criticality, or it is said to be in critical condition when K is equal to 1. If value of K is greater than 1, that is number of emitted neutrons is more than number of incident neutrons, then the nuclear reactor is likely to have explosion inside and it may cause lot of damage also. In that case, the nuclear reactor is said to be in a state called supercritical state. Supercritical stage. Correct? Supercritical state. And if value of K is less than 1, then nuclear chain reaction is likely to get stopped and we will not have the emission of energy with the constant rate. Then that reactor is said to be in a condition called subcritical state. I repeat, if K is equal to 1, nuclear reactor is said to be in a critical state. If K is greater than 1, reactor is said to be in supercritical state. If K is less than 1, reactor is said to be in subcritical state. Got it? Now, when the value of K is increasing more than 1, what we do? We just insert the rods made up of cadmium and boron inside the nuclear reactor, and these rods have one specific property. They can absorb excess number of neutrons. Once the excess number of neutrons is absorbed, naturally value of K will decrease, and after that the rods are withdrawn from the nuclear reactor. So what these rods do after getting inserted into the reactor, they control the number of emitted neutrons. Because they control the number of emitted neutrons, we call them controlling rods. So these rods made up of cadmium and boron, they are called controlling rods. Okay. Taking care of all these safety measures, scientists in India have prepared 4 nuclear reactors which are right now operating at a place called Trombay, which is a place near Bombay, correct? In the institute called Bhabha Atomic Research Center, these all nuclear reactors are being in the operative conditions right now. Okay, thank you. Come on, my dears, let us study now next short note. It's very interesting, very important also, about nuclear reactor. See, in our syllabus we have to study about that nuclear reactor which is used in power plant, and here in the figure you will find line diagram of that nuclear reactor which is used in power plant. Okay, fine, using which we just produce electrical power. Okay, fine. Now here it is a composite system of different stages in which different form of energy is being converted into another different form of energy. How? I am showing you. Here we find fission chamber in which there is a fuel which is normally 92 uranium 235. Okay. Actually in practice we find uranium having these two isotopes. One is 92 uranium 235, another is 92 uranium 238. Now, this particular uranium, which is useful here, is obtained in nature with a very small proportion, roughly approximately 0.7 percentage, which is a very small proportion. Okay? Through some proper processes, we just enhance this amount, we increase it to nearly 3%, and such uranium whose quantity has been increased is known as enriched uranium. Enriched uranium. Okay? Such enriched uranium becomes the core for the working of this nuclear reactor. Okay? What is the principle of working of nuclear reactor? Controlled nuclear chain reaction process. Controlled nuclear chain reaction process becomes the principle for working of any nuclear reactor. Okay? If you have uncontrolled nuclear chain reaction, then it becomes a principle of working of nuclear bomb. Right now we are discussing about nuclear reactor, in which there is a controlled nuclear chain reaction. Got it? Fine. Now, what are these? These are the controlling rods. Controlling rods. Controlling rods. Last time we had discussed about it. They are used for controlling the number of neutrons. They are made up of cadmium and boron. They are kept in this fuel. Got it? Surrounding to this core, we have moderators and neutron reflectors. Moderators and neutron reflectors are kept here. Fine. Now, first of all, we allow this nuclear chain reaction to take place, and through which we get enormous amount of heat energy. Actually, it is obtained through the conversion of nuclear energy into heat energy. Nuclear energy into heat energy. Fine. Now, using that heat energy, we just raise the temperature of water which is passing through this tube. Okay? We raise the temperature to nearly 600 Kelvin. Though this temperature is more than 100 degrees centigrade, then also it is not the boiling point of water, because the atmosphere, the pressure is not 1 atmosphere. Pressure is very high pressure. At very high pressure, the boiling point of water is higher than this. So, still water remains water only, but its temperature is 600 Kelvin. Okay, fine. Now, pressure is nearly 150 atmosphere. So, we obtain water here with a very high degree of temperature and very high pressure. Now, using that very hot water, we just convert the water into the steam which has been entered in this vessel, which is called steam generator. In this steam generator, whichever water is entered, that water is being heated up to the boiling point of water. So, finally, that water will be getting transformed into steam, and that steam is allowed to pass through this tube. Okay. In that steam, we have highly energetic molecules of vapor, highly energetic molecules of steam of water, and they have lot of kinetic energy. Kinetic energy, you know, it is a part of mechanical energy. Now, tell me, using that mechanical energy, what we do, we just run this turbine. Okay, turbine is some sort of wheel, and using that mechanical energy, if you are running the turbine, then along with the turbine, this armature made up of copper coil also starts rotating, and because it is rotating in a magnetic field, as we have studied in the previous chapter, it is none but electric generator, in which the working is based upon the principle of electromagnetic induction. Because of change in magnetic flux of this armature, you will have some induced EMF across the two ends of the coil, and finally that induced EMF is nothing but generation of electrical power. So, we get electrical power between these two terminals which are brought out. Okay, fine. So, here mechanical energy is being transformed into electrical energy. Fine. Now, after the steam does the work, naturally the steam, the pressure will be low also, and steam is getting cooled down. Steam is getting cooled down. Here pressure of the steam is very high, here pressure of the steam is low because it has done some amount of work. This steam is cooled down also further. Now this cold steam, I mean the temperature of the steam goes down and further it is being cooled down by this water which is allowed to enter in this tube. Here is a cold water. Because of contact with the cold water, this steam is being further cooled down, and when the steam is being further cooled down, finally it will be transformed into water, and that water is allowed to enter into this steam generator through this pump. What does this pump do? It creates here high pressure and here low pressure, so water will rush from high pressure to low pressure. Okay. So here the working substance was initially in the form of water, and once again at the end of one cycle it comes in the form of water only. So a thermodynamic process in which working substance is allowed to undergo a series of processes and finally brought back to its initial state. Such a process is known as cyclic process, correct? So here cyclic process is being performed. Okay, fine. Now tell me, this hot water raises the temperature of cold water which is entering here and transforms it into steam, and finally that water will get cooled down, and that cold water using this pump we just pressurize it to just rush it to just flow inside this core. Okay, because here the flow of water is due to pressure difference, we call it pressurized water reactor. Pressurized water reactor. Got it? Fine. Tell me, in which stage energy in which form is getting transformed into which form? Here nuclear energy is being transformed into heat energy. Here heat energy is being transformed into mechanical energy, and here mechanical energy is being transformed into electrical energy. That's what I written here. Nuclear energy first of all gets transformed into heat energy. Heat energy gets transformed into mechanical energy, and finally mechanical energy gets transformed into electrical energy. Okay, fine. Now they have talked about 92 uranium 238 also in the textbook. Let me talk about that. If you have this isotope of uranium 92 uranium 238, and if you bombard it with neutron, it gives you first of all compound nucleus which is rather excited. It is 92 uranium 239, and finally it gets divided into 93 neptunium 239 plus electron is emitted and anti-neutrino, nu bar, anti-neutrino. Now this 93 neptunium 239, come on, it gets transformed into 94 plutonium 239 plus electron is emitted and anti-neutrino is emitted. This plutonium 94 plutonium 239 is found to be highly explosive and is also highly radioactive. Got it? My dears, please do lot of practice for drawing this figure. Is really difficult. Draw it minimum 5 times, please. My dears, in this setup, this part in which nuclear energy is transformed into heat energy is known as primary loop. What is it called? Primary loop. And the rest of the part of this nuclear reactor in which that heat energy is ultimately converted into electrical energy, that whole part is known as secondary loop. Secondary loop. Okay.